All right, let's just jump right in because we're about to unpack something that's, well, it's pretty unsettling. We're going to look at how one of the most common, most trusted statistical tests out there might be, in a way, lying to you, to scientists, and to pretty much everyone who relies on data.
Now, everything we're diving into today is beautifully laid out in the book From Data to Insights by Gianmarco Alberti. If this stuff fascinates you, you're definitely going to want to check it out. We've got the link right there on the screen for you. It's an incredible resource.
So let's kick things off with a pretty bold question, taken straight from the source material. What if the gold standard test, the one used in thousands upon thousands of studies, is designed in a way that can systematically create a statistical illusion? What if it's telling us we found something huge when, really, there's nothing there at all? To really get our heads around this, we're going to walk through a little statistical puzzle. It all starts with one of the most famous datasets in history, but we're going to look at it with a twist. Okay, so here's our first table. It's a tiny snapshot from the Titanic, just 38 passengers. You can see it's split by gender and whether they survived. We've got 19 males, 19 females. For the guys, 9 died, 10 survived. For the women, 10 died, 9 survived. Just soak those numbers in and really pay attention to how small the group is. Only 38 people.
Now, look at this second table. Same setup, but this time it's for 3,800 passengers. That's 100 times bigger. Here, 900 males died and 1,000 survived. And for the females, 1,000 died and 900 made it. The numbers are obviously way bigger, but look at the pattern. Does anything seem a little familiar?
If you actually crunch the numbers, you'll see something wild. The proportions are exactly the same. In that tiny data set and in this massive one, the survival rate for both men and women is hovering right around 47%. The fundamental relationship is identical. So you'd think any statistical test worth its salt would give us the same exact conclusion for both tables, wouldn't you? Well, this is where things get really weird, because the results aren't just a little different. No, they are polar opposites. Let's see what happens when we unleash the standard, workhorse statistical test on this data. The test we're talking about is the chi-squared test. It's the go-to tool for figuring out if there's a real connection between two things, like gender and survival. So let's ask it, what's the deal with our two tables? And here are the results. For our small group of 38 people, the test comes back and says, nope, no significant relationship here. The p-value is huge, 0.746, basically saying this is just random noise. But for the massive data set, with the exact same proportions, the test practically shouts, this is a highly significant relationship. The p-value is a minuscule 0.001. How is that even possible? This isn't a glitch in the matrix. This is a core feature of the test itself. It's something we're going to call the sample size trap. So let's pull back the curtain and see how this statistical magic trick is done. Okay, here it is. The chi-squared test's dirty little secret is that it's incredibly sensitive to the number of people in the study. The way the math works, as your data set gets bigger and bigger, even the tiniest, most meaningless differences get amplified. A tiny whisper of a difference in a small data set becomes a deafening roar in a large one. Let's go back to our small table for a second. With only 38 people, the tiny difference between what we saw, say 10 men surviving when we might have expected 9.5, it's statistically invisible. The test just kind of shrugs and says, could be anything. It's probably just random chance. But what did we do to create our second table? It was simple, right? We just took every single number in that first table and multiplied it by 100. We just blew it up, keeping the proportions perfectly intact. And by doing that, with this much larger sample size, that same tiny proportional difference suddenly looks like a giant to the statistical test. A deviation that involved maybe one person now involves hundreds of people. So the test sees these huge numbers and screams, this is earth-shattering, it's highly significant, even though the actual relationship between gender and survival hasn't changed one bit. So you might be sitting there thinking, okay, that's a neat little math trick, but this is so much more than an academic puzzle. This sample size trap has huge, real-world consequences playing out every single day. I mean, think about it. You can have government policies being shaped by significant findings that are actually meaningless. You've got huge companies making massive business decisions based on a tiny customer preference that just looks big because they have tons of data. And, maybe the scariest of all, this leads to misleading medical studies. Let me give you a really scary example. Imagine a drug is tested on 100,000 people. It's found to have a 0.01% improvement over a sugar pill. Because the sample size is so huge, that result can be statistically significant. The company can legally say, our drug works. But is a 0.01% improvement actually useful to anyone in the real world? No way, of course not. So what do we do? How do we get out of this trap? How do we tell the difference between something that's just a mathematical curiosity and something that actually matters? Well, it turns out the solution is to start asking a much better question. See, statistical significance, that p-value, it's really only asking a very basic question. Is there any kind of relationship here that probably isn't just random luck? That's a really low bar. The much smarter, much more useful question is the one asked by what we call effect size, which is, okay, fine, there's a relationship, but how strong is it? How much does it really matter? That is exactly what effect size measures. It's a number that tells you the real-world strength or magnitude of a relationship. And here's the beautiful part. Effect size is totally immune to the sample size trap. For our two Titanic tables, the p-values were all over the place, but the effect size would have been the exact same for both. And in this case, it would have been tiny, telling you right away that this relationship is trivial and not worth your attention. And all of this brings us to the single most important point of this entire explainer. We can protect ourselves from this kind of statistical sleight of hand. All it takes is one simple, powerful, critical question. Here it is. This is the big takeaway. The next time you read a headline or see a study that's bragging about a statistically significant result, just stop. Don't be impressed. Instead, arm yourself with the follow-up question. That's cool, but what was the effect size? How strong is this relationship really? Because once you understand the difference between statistical significance and practical importance, you can't be fooled anymore. It's the difference between being manipulated by data and actually understanding it. So I'll leave you with this thought. The next time you see those highly significant results, what are you going to ask?